Okay, this is what we're doing for recitation this week. We're not holding recitation like we usually do because we're grading the exams tomorrow. So instead, I'm going to just do a little screencast here for what we would have gone over during recitation. So first, I'm going to go over the implementation of a problem that could end up looking similar to how cryptarithms might look. And then I'll go over some specific details for cryptarithms. Okay, first, permutations. Permutations is a problem where you're taking in a list of integers, let's say 1 and 2, and you're supposed to return a list of all of the permutations of those integers. So just for example here, the list we should return would be the list containing 1, 1, 2, 1, 2, 1, and 2, 1, 1. That's the entire list of integers. You'll note that we have two 1s here, but we don't include permutations where the order of the 1s matters. That's because they're identical, so we're just counting unique permutations here. We're ignoring the duplicates in terms of order, but we are counting the duplicates in terms of number. And that fact gives you a hint to the first step of implementing this. The first step, and I should note that there are multiple ways of implementing this, but in the way I've done it and the way that might be useful for you to think about in cryptarithms is where we first set up a count for each of the digits that we have. So here in this example, we have the following counts. We have the number 1 2 times, and we have the number 2 1 time. Okay? So that's our counts. And now that we've counted all of the digits that we're dealing with, we can use this data structure to recursively generate permutations. And so we're going to do that by taking things out of this counts map and putting them in a given permutation. So let's say our permutation starts as empty, and then we take one of the 1s. So we take a 1 and we put it here, and then we would decrement this count. Okay? And then we can do that recursively. So now we'll take another 1. So now we have 1, 1, and we'll take another 1. We'll decrement this count down to 0. And now that the count of 1s is 0, we'll take the next thing. We'll take a 2. And so this will become 1, 1, 2. We'll decrement this to 0. And now we've reached our base case because we have nothing left to take. So this would be one permutation. So we've got a permutation, but now the trick is going to be to generate the other permutations. And so what we'll do is we'll record this permutation for our output, but then we'll return from the function, which means we're popping up the call stack. And so we'll return to the function that we were in. And now what we want to do is we want to put this 2 back, and we'll take this 2 out of the array. Now we're back to here, and we can ask ourselves, is there anything else we could do at this step? We're trying to generate all the permutations, all the possibilities. So here we took a 2. Is there anything else we could have done? No. So we're done with this iteration, and so we're going to return up the call stack again. Okay, so we take this 1 off here, and we return a 1 over here. So now we have 1, 1. Okay, so now we're dealing with 1, 1 and 1, 2. Now do we have an option? Now we do. At first we took the first 1 here. At first we took this 1. And that led to the first permutation we had right here. Now this time we're going to take the 2 instead. And so we're going to take the 2, so we're going to decrement its count to 0, and our array is going to become 1, 2. Okay, now we're going to recurse again. What's the only thing we can take? Well, we can take a 1, so we're going to decrement that to 0. Now we have 1, 2, 1. And now we've reached our base case again. We have another permutation. We've gotten the second permutation here. Okay? So we're going to return. We're going to pop up the call stack. We're going to remove this last element from the permutation. We're going to be back up to here. And we removed a 1, so we better put a 1 back in our map. All right. Now, the first time through, we picked a 1. Is there anything else we could have picked? No. So we go back again. We go back to our first permutation. Now we're back to this situation. We picked a 2 before, so we return a 2 to the map. So now we're back to the situation where we have 1, 1 on our permutation. And we have 1, 1 in our map and 1, 2 in our map. And so now we have to ask ourselves, do we have anything else we could do? And the answer is no, because we tried taking a 1 next. We took a 1 next. And then we tried taking a 2 next. And that's it. That's all we can try. So we're going to return again. We're going to return all the way back up to the scenario where we have nothing on our permutation, which means we're going to take off the things from the map accordingly. All right, now we're back at the beginning. And we know that we need one more permutation here. We need this permutation. And how would we get that with this algorithm? Well, we first tried taking a 1 as the first element. Now we'll try taking a 2. So this will go, we'll put a 2 onto our permutation. And we'll take a 2 out of the map. And we'll repeat until we get our last permutation. So that's how this algorithm works. Let's actually look at the code. And hopefully looking at this code will give you some insights as to how you could implement cryptarithms in a similar way. So we're looking at this permutations code. I've called the function permute. It takes in an array of numbers, just like how we said. The first thing we do is we make a data structure for our output. Our output is a list of integers. That makes sense, because each permutation is a list, and we're returning a list of those. And then we call our main recursive helper function generate. And we call it on the counts of each integer. We've put that into a helper function. And on a new data structure here, a stack, this is how we're going to represent the permutation so far. And then this is the data structure that we're putting our output in. You'll note that Java is passed by reference, and so this data structure, when we pass it in, that data structure, any modifications we make, those modifications will retain. So we're going to compute our result by putting things into this result data structure and then returning it at the end. Okay, so we can look at account occurrences here really quick. We go through the numbers. We make a hash map, first of all, from integer to integer. And then for each number, we put that number into the hash map with a value of the previous value plus 1. So we basically increment the value at that index in the hash map by 1. And if there's nothing there already, we put a 0. So this is going to count the number of times each number occurs in nums. So now that we've got this map, let's look at the heart of the algorithm here, the generate function. First of all, we need to know if we're in our base case. That's the first step of any recursive function is, are we in a base case? Here we said on the tablet that the base case is when we have nothing else to put in our permutation. And we knew that when our map had nothing that had a positive count. So we're going to loop through our map. We're going to loop through all the keys of the map and get every value. These are the number of occurrences we have remaining. If it's greater than 0, we're not in our base case, so we can stop looking. If we get through this entire for loop and everything was 0, then we're in our base case, and we can add the permutation to our result. One thing to note here is, like I said before, Java is passed by reference, and so this permutation variable that we're passing in is a reference, and on the tablet, we were taking the permutation and removing things from it when we popped up the call stack. And so if we're removing things from that permutation, we don't want that to affect the result. The result should save the permutation as is right now. And so we're going to clone the permutation. And that's going to allow us to modify it later. Okay, so now we've done our base case. Now what's the recursive case? The recursive case is that we did have something in our map that we could add to our permutation. And so let's loop through those things and try adding them to the permutation. So we're going to loop through all the values that we have and check to see, do we have one of them? So if the number of occurrences of a given value is greater than 0, then we have one of them that we can put into our permutation. So we're going to take that thing that we have at least one of, and we're going to replace its count with its previous count minus 1. We're going to decrement the number that we have. And that's because we're taking it and putting it onto the permutation. Okay, now we actually have to put it on the permutation, so we're going to push it onto the stack. And then we're going to recurse. And again, Java is passed by reference, so all of these things we're passing in here are passed by reference. They're going to maintain the state that we just added to them. Okay, after generating, we need to undo everything we just did so that we don't affect other recursive calls. So we're going to pop from the stack, and we're going to add 1 back to that element in the hash map. And that's it. That is the entire algorithm. So let's just try running it. Here I'm running it on the permutation. Here I'll take off this last element, so it's exactly the same as the example that we had before. And here we go. I need to hit run. Oh, that's running something else. Okay, one moment. Run permutations. Okay, and we got exactly what we expected. We got 1, 1, 2, 1, 2, 1, and 2, 1, 1. So this is a way of generating all the permutations of a list with duplicates without repeating any permutations. And we used mutable data structures in order to do it without wasting a lot of space and pretty efficiently. So hopefully that implementation will help give you some ideas for how you might implement Cryptarithms. Cryptarithms is probably going to be one of the harder problems that you've seen so far. And it's because the implementation is tricky. You're going to be dealing with, I mean, depending on how you do it, there's multiple ways. But it's possible that you'll be encountering mutable data in recursive calls. And that's always hard to deal with because when you're recursing over mutable data, you have to consider every possibility. You want to make sure that you're always returning your mutable data to a consistent state after every recursion. So just be aware of that and be very careful. 0, 1, 7. Okay, now we're back. Okay, finally I'm going to just talk briefly about Cryptarithms itself because it's a cool problem. So Cryptarithms is a problem where you're given an addition problem, but where all of the digits have been replaced with letters. And so your output is going to be a map from letters to numbers that letter should represent to make this addition valid. So S might map to 3, E might map to 4, ... One trick here is that each letter needs to map to a unique value. So you can't, E here could not map to 3. That would be invalid. Because then we'd have 2 different letters mapping to the same value. And this actually ends up being a nice property, and you'll probably realize that when you implement the solution. Okay, so in terms of ways of solving this problem, the obvious thing that you could do is you could just try any combination of mappings. So you could say, what are all the characters that we have to map? Well, we have an S, we have an S, we have an E, we have an N, a D, an M, an O, an R, and a Y. I think that's it. I'm probably missing one. But you can just try different mappings. So we could say, map that to 0, map that to 1, map that to 2, map that to 3, and then check. Okay, is this a valid addition problem now? And one thing to note is that we actually, in the test file, we wrote a function that does test if a mapping is valid for a given problem. So you can copy that code if you want, but it's not too hard to write it yourself. Basically just look up each one of these characters in your hash map, create this number, create that number, create this number, and check to make sure that they do add up to each other. So that's the naive brute force solution. We're just going through every single possible mapping. But there's a better way, and it has to do with backtracking. The reason it has to do with backtracking is because we don't have to assign all of the characters at once. We could just assign M to something and R to something, and leave everything else blank. That's a partial solution. And you'll remember from the backtracking lecture, partial solutions is one of the requirements for backtracking. So we have partial solutions. Now the other question is, can we determine if a partial solution is invalid? Well, for this example, let me give you an example of a partial solution that is not valid. So let's take this partial solution. D maps to 1, E maps to 2, and Y maps to 4. Okay? You can probably already see why this is invalid. If D maps to 1, then we've got a 1 right here in the last column. We've got a 1 right here. E maps to 2, so we've got a 2 right here. And Y is a 4, so we've got a 4 right here. Now, regardless of whatever the rest of this number is, we know that this is invalid because 1 plus 2 is not 4. So we can backtrack in this case. If we have this map and we're working with this problem, then we can backtrack because we know that anything else we try is going to be invalid because this addition is just not valid. There's nothing we can do to change that. So this would be a backtracking case. So the takeaway here is that you might want to think about columns as a way to solve this problem. And you might want to think about ways that you can represent those columns with efficient data structures in order to make your implementation more easy. Strings are hard to deal with because they're immutable. If you try to change a string, what you're actually doing is making a new string, which is going to require linear time and linear space. So I would consider converting your data, your input, into some other data structure that's easier to deal with so that you can think about the problem in terms of these columns, because that's going to help you implement the backtracking. That's all I had prepared, so I hope this was helpful. If you still have questions, definitely come to office hours. We hold a ton of office hours on Wednesday, and make sure to book ahead. And yeah, good luck.